Today we're going to look at reverse phase levitation by a ring of 11 magnets and a 1.25 millimeter pancake coil. You can see it's going to attract like that. When we flip on the power in one direction, these two objects attract. We flip the leads and watch them repel. So that's just what we saw before for vertical interactions, and now we're just looking at horizontal interactions of these two objects. Now we know this is reverse field levitation and not forward field because the north side of this magnet N attracts this coil when it gets turned on, and that's the center of part of the field here, so it's being attracted north-south, north-south, and the magnets around the outside, the permanent magnets are all S, and it repels them. We switch the current and this pancake coil repels. Now it's a south magnet on this side, and it repels the north field at the center, and it attracts the magnets on the outside. So in both cases, this pancake coil is interacting with the field, reverse field here at the center, and not with the forward field around the edges of all these magnets. So this is just what we saw before, having everything vertical, but now it was horizontal instead. We can also measure repulsions by Lenzs Law for this kind of coil. But the effects are rather weak. Using this big sheet of aluminium next to the pancake coil to look for Lenzs Law repulsion. When we flip it on, we can hardly see anything at all. Just this tiny effect. Way too weak to use functionally. Now if we use AC current at 120 volts and 2 amps instead, with this 0.5 millimeter pancake coil, we can get a lot more Lenzs Law repulsion power. Oh, that's more like it. Turning AC current on and off at 120 volts from this 0.5 millimeter pancake coil. Likewise, if we have a disc of copper about the same size, 2 mil thick, next to this 0.5 millimeter pancake coil, we put 120 volts and 2 amps through it to get Lenzs Law repulsion. We get quite nice motion of the copper away from the pancake coil. So this is a quite reasonable Lenzs Law effect. We may be able to do something with it. Several ways we can hook up this 0.5 millimeter pancake coil inside 11 magnets with 120 volts. This is simply a repel pulse. Now with this 0.5 millimeter pancake coil inside 11 magnets, we can put 120 volts also by switching the leads as an attract pulse. Put it apart a little and watch the attract pulse. So it can either attract or repel depending on how we place the leads. This pancake coil is still wired exactly as in the attract pulse for a ring of 11 magnets, but if we put a sheet of aluminium there instead, we get Lenzs Law repulsion, and it repels significantly. Repel and attract. It can repel aluminum, but it attracts other magnets of the same polarity. Now let's just switch the coils one more time and make sure the Lenzs Law the other way also repels. Flip the lead, still a sheet of aluminium. We again, to opposite polarity, gets Lenzs Law repulsion again. It still repels. Flip them one more time to confirm. The lead's back for a second time just to confirm it still repels, and it does. So no matter which way the leads are arranged, this pancake coil will repel a sheet of aluminium. But if we flip the leads with a ring of permanent magnets, it can either attract or repel. Then we have two different magnetic phenomena here to consider. Today we're going to study Lenzs Law repulsion of a 3 millimeter, 200 millimeter wide aluminum plate by a 0.5 millimeter wire coil with different voltages and polarities. Now this is 120 volts AC. Next, for this 0.5 millimeter pancake coil and 3 millimeter aluminum disc, we're going to look at 120 volts AC from an isolation transformer put through this 35 amp bridge rectifier to produce a DC pulse. It's much weaker than AC, isn't it? Now we have a variac running at 240 volts mains power and a switch to control it. And we're going to flick the switch and see what happens to the lens. Quite an impressive effect. 240 volts works a lot better. This is 240 volts main power, and it gives you a very nice Lenzs Law effect. Now that's AC. We're going to try to rectify it and see what happens. We have the same 0.5 millimeter wire coil. We're going through a switch and a 35 amp bridge rectifier, and we'll see what happens. Pretty good power, but not quite as strong as full AC. Study briefly the voltage dependence of Lenz's law. This is 240 volts. Big effect. So we're going to look at 120 volts AC. Smaller effect. Now we're going to look at 60 volts AC. It hardly moves. Next we're going to test the power of Lenzs Law repulsion with a 0.5 millimeter pancake coil and various size aluminium or copper disc. Here's a 200 millimeter aluminium disc. Quite a lot of power there. Here's a 150 millimeter aluminium disc. Just about the same. Very good Lenzs Law repulsion, 240 volts AC power. Here's a 100 millimeter aluminium disc. All about the same. It's not the size of the disc, but how far the magnetic field gets weaker as it moves from it, the Lenzs Law repulsion field. Here's a small 60 millimeter piece of aluminium. It doesn't repel very much from the center of the very small field. Next we'll try some copper. Here's a 110 millimeter piece of 2 millimeter copper. Quite good field because copper has a high electric conductivity and repels well. Here's an 80 millimeter piece of copper that's 2 millimeters thick, 240 volts AC from a 0.5 pancake coil. Again, very nice Lenzs Law repulsion. Finally, here's a 60 millimeter piece of copper that's only 1 mil thick. It doesn't repel very far. Either the thinness or the small size doesn't give much Lenzs Law repulsion. Once again, is a ring of copper 2 millimeters thick, coming off a normal coil, not a pancake coil. It's 110 millimeter, just bigger than the coil itself. Quite a big repulsion effect. We're going to try a slightly different experiment. We've taken the 0.5 millimeter pancake coil and a 110 sheet of copper, and we put a ring magnet on the back side of it. So we'll put it up close. And I had to turn the voltage down from 240 to 120 for this experiment. In DC, going through a rectifier, out of the variac into our rectifier, because it was just about to blow the power leads with 240. So we're using half the power as before. We'll turn on DC through a rectifier and watch what happens. Now that's when the magnet and the Lenzs Law are going the same way. Next we'll flip the magnet and do it the other way. Now we flip the magnet the other way, so the magnet wants to attract and the copper wants to repel. The magnet's overwhelming the Lenzs Law, pushing it in, so let's try a smaller magnet. Now, in order to explore the relation between magnetism and Lenzs Law, we've taken 4 small test magnets of 10 millimeters each and put them in the outside, near the very center of a copper disc with a pancake wire coil behind it, all in the same polarity. We turn on 120 volts DC and watch what happens. There's quite a nice repulsion because the magnetic fields of those 4 magnets adds to Lenzs Law repulsion. Now we're going to flip the magnets and see what happens. If we take those same 4 magnets on the inside that have just made it repel a long way and just flip them over so they attract rather than repel, we turn on the power and it just attracts. But there wasn't much effect on the inside. It'll attract on the inside but not on the outside. And that's the relation between the magnetic forces and Lenz's law. The magnetic forces are much stronger, and they can either add to Lenz's law of repulsions or they can subtract from them, as we've just seen.